What will happen to Arctic precipitation rates as temperatures continue to rise? Hello friends, Jim here. Well, Arctic precipitation rates are expected to double as the temperature rise, finds a new study. We'll take a look at this figure in a moment. First, some background. The Arctic is often cited for a plethora of impacts resulting from anthropogenic climate change, including glacier retreat and reductions in floating sea ice, meltwater incursions, changing ocean salinity, as well as sea level rise, to name but a few. As the region is warming 4 times faster, some places 5 times faster, than the global average annually, ice albedo feedbacks will only exacerbate the issue further. This mechanism focuses on melting ice, exposing more, quote-unquote, dark surface ocean and land to absorb heat, causing further melting, further warming, versus with the reflective nature that typically sea ice and snow covers would provide. Precipitation in this icy region, you have several continents there. This is really an inaccurate statement to say icy continent. That's Antarctica. You have the Arctic Ocean up there. So precipitation on this icy region predominantly falls in the form of snow, both in winter and summer, but occasional rain can occur with the transport of warmer air. I did a video some time ago. It was a deep dive video where I discussed how by 2100, snow may very well be a thing of the past in the Arctic region. That all precipitation will fall as rain, freezing rain, that kind of stuff. No more snow. So you may want to check it out if you haven't seen it yet. And, just here in Alaska, October and November in recent years, actually going back almost 20 years, we're getting a lot of freezing rain events. Let me tell you, that is not fun. And I think just this past winter, I don't think we got any freezing rain. But then this past winter has been, compared to recent winters for Alaska, been a cool one. It's almost like a throwback to what it used to be. We had like several weeks of 40, 50 below, that kind of stuff. So things are changing rapidly in the Arctic. While it is universally acknowledged that current low precipitation patterns are likely to change with global warming, the extent of the rate of increase is continuously being defined and is the focus of a new publication in Geophysical Research Letters. Precipitation patterns are changing. Dry areas are getting drier, wet areas are getting wetter. So we're seeing this now. So scientists at Japan's Meteorological Agency and National Institute of Polar Research have discovered a rapid increase in Arctic precipitation at twice the rate of rising global temperatures. The two factors are proportional. As Earth's temperature increases, so too will the rate of precipitation. Remember, for every increase of 1 C in atmospheric temperature, the atmosphere can hold approximately 7% more water vapor. This pattern was exhibited most prominently during Northern Hemisphere autumn months, September through December, compared to summer months, June to August. To determine this, lead researcher Seiji Yukamoto and the team used coupled model intercomparison project phase 6 models, CMIP for short, right, to determine a trend since the 1980s, with a clear strengthening of the temperature precipitation link in this time frame. And they established, according to their model that they use, they established an Arctic amplification factor of 2.7 for temperature as a ratio of Arctic to global mean temperature trends, and 6.3 for Arctic to global precipitation trends. In addition to these changes in greenhouse forcing, there was a coincident plateau in anthropogenic aerosol emissions, such as from burning fossil fuels. Prior to the 1980s, these aerosols had a dampening effect on the growth of greenhouse gas concentrations as they assisted cloud formation and the reflection of incoming solar radiation, therefore helping to keep the planet cooler. However, the models clearly show that since the 1950s, as anthropogenic aerosol concentrations declined up to the 1980 plateau, greenhouse gas forcings increased. Now, there's some kind of differing thoughts going on here. The aerosols that were released as a result of burning the fossil fuels before the regulation, the aerosols provide what's called the hygroscopic particles by which water vapor, water molecules can basically coalesce around. And so basically, you cannot really form a water droplet unless you have hygroscopic particles. Well, we get enough water droplets, you get a cloud. And when the water content gets heavy enough, those water droplets, whatever form it may be, rain, freezing rain, sleet, hail, snow, what have you, will eventually become heavy enough to basically be subjected to gravity and fall back to the surface. Well, if you don't have the aerosols, you don't have these hygroscopic particles. Therefore, the abilities to form clouds, to form the water droplets, to coalesce around said particle, is reduced, thereby reducing cloud formation. And therefore, the thinking for those who push the aerosol effect, which it does impact the atmosphere, it just doesn't impact the oceans. And I'll get to that in a moment. But, so basically saying if there's no clouds, then more sunlight energy, more absorption of the short wave can take place. Well, you also have mesoscale eddies that are mixing the interface between the atmosphere and the ocean, mixing a lot of that heat energy we put into the atmosphere. Remember, the oceans have absorbed over 93% of the energy humans have released as a result of burning fossil fuels. The atmosphere, only 2%. So what's happening is you have all this heat in the oceans, it's evaporating. And even though the gradients may be weakening from equator to pole, there is still going to be some movement. You're still going to get cooling as, you're going to have these water vapor in there. It's still going to eventually cool as the temperatures cool as you move further north. And you're going to get precipitation. So basically, it may take a longer time frame, whereas the aerosol particles may increase, speed up the process of cloud formation and so forth. But let's not forget phytoplankton's role. They release dimethyl sulfide, aerosols, to regulate, and it's shown to be a planet regulatory temperature mechanism. And DMS releases increases the planet's warmth. In other words, it's a negative corrective feedback loop. So the phytoplankton's a very important role. What is also, I don't think, considered here is all the fires we've had. Fires release a lot of particulate into the air. They release, from the burning action, they're releasing aerosols, soot, so forth. May be heavier, may not persist as long, but it's still there, and it still is going to counter the reduction in aerosols from burning the fossil fuels. And then don't forget, every so often you get a volcano going poof, throwing some stuff up into the atmosphere. So it's interesting what they're reporting, and there definitely are changes to the precipitation patterns. Furthermore, a combination of increased radiative cooling, that's the long wave, right? Infrared back out to space, to balance the absorption of shortwave from the sun and reduce poleward sensible heat transport. That's moving warm water from the tropics to the pole due to smaller pole equator temperature gradients have enhanced the Arctic precipitation pattern further. Basically, the air is getting colder over the Arctic, and colder air, condenses more readily. And that ties into the point I was saying earlier, that you get all this evaporation from the ocean surfaces. As it moves north, it's in the to where the air temperature is cool, it's going to condense. So, extrapolating this knowledge to examine further future trends up to 2045, the research team determined current precipitation patterns will continue, and beyond this, the 2100 precipitation increases may be suppressed by reduced emission predicted declines in temperature increases. Pipeline warming, lag effects, ocean heat content, no, that's not realistic. So now let's take a look at this figure here. Okay. So the top two panels, A and B, is for the Arctic, right? Looking at surface air temperature, precipitation. The bottom two, worldwide. Okay. So let's see, model changes in surface air temperature precipitation for the Arctic, A and B, compared to global averages, C and D. Okay, C and D. Not sure why they have 60 to 90 in here. That should probably be up here. If this is the Arctic, they should have 60 to 90 up with panels A and B. That's an oopsie. Big oopsie. And they give the anomaly in temperature Kelvin. Okay. And then the precipitation as a percentage. And what we can see here is, and they're looking from the period from 1980 afterward, we can see a major increase in air temperature. And with that, a major increase in the precipitation. And remember we talked about, they said, where was it? 6.3 for the Arctic to global precipitation, 2.7 for the temperature. Okay, 2.7 thereabouts, right there. We can see it right there. And 6 point, we can see it right there for the precipitations, right off the charts there. And then you compare that to global. Now, this shaded area is the 95% confidence interval. Here's the aerosol. You notice the big error around 95% is a reflectance of error. The big error around the aerosols. And the black line is historical, and the red line is historical, including greenhouse gases. So they're contending that surface air temperature is increasing much more rapidly than the rest of the planet, which is true, and therefore precipitation rates are also increasing much more rapidly at a higher rate than the rest of the planet. So, what are we to make of this? If I can kind of pull together some of the various concepts I've tossed out there. Aerosols help form clouds because of the particulates they introduce. The clouds, it's a double-edged sword. The top of the clouds will reflect the short wave coming in, so it has a cooling effect, but the bottom of the clouds traps the long wave. So it has a warming effect. You have to keep that in mind. Reduce aerosols, presumably reduce cloud formation. Well, now more sunlight energy can warm up the air. Okay. Will it warm up the ocean? No. For reasons I've discussed before. Specific heat of water is much, much higher than air. And the projections are warm up the air by 0.42 C by, over 100 years. That you ain't going to warm up the sea surface temperature by 5 to 7 C. Okay? But thanks to mesoscale eddies acting as the interface between atmosphere and ocean, and there are mesoscale eddies all over the place, this facilitates the entrainment of heat, CO2, etc., into the oceans. Well, now that heat energy is going to do something. Well, the oceans are stratifying. So what's that heat energy going to do? It's going to move up laterally. It's going to move poleward. It's going to move vertically upward, warming, increasing sea surface temperature, and continuing to diffuse to the atmosphere, warm into the atmosphere where you get some evaporation as well. It also forms cyclonic storms that distribute, energy. You have a bunch of precipitation events moving moisture around. But you get that, energy into the atmosphere. It starts moving northward due to the atmospheric cells, like the Hadley and the Ferrel cells, right? And then it takes it to cooler regions where, it condenses, and then you get precipitation. And as I said earlier, you cannot dismiss the role of phytoplankton. You cannot dismiss the role of wildfires. So, in my view, with the role of phytoplankton and wildfires, they could counter the reduction of aerosols from burning fossil fuels because they introduce probably a replacement amount. And don't forget, there are other different types of aerosols, not just SO2. You got the nitrous oxide, right? You've got other types of particles that can act as aerosols, that can form the needed impetus to form the water droplets and so forth. But the thing to keep in mind is that the precipitation rates are doubling in the Arctic, and because the planet is warming so much, the projections are by 2100, snow will be a thing of the past in the Arctic. And that means we're going to have a runaway warming planet. That, to me, is the real concerning aspect of all of this. So, this is very interesting. Thank you for your time. Until next time.